I'm warming up to do the wave because we're talking about electromagnetic radiation. Hit the theme.
Ain't nothing but a chem thing, baby. Two flipped out teachers going crazy. Lancaster is a district that pays me. Unbreakable, so please don't try to break this. But back to the lecture at hand.
Hello and welcome to another episode of SchuFu Chemin at ya. I'm your host Shu, and with me as always is Fu.
What up, nerds?
Dalton.
Hard sphere.
Thompson.
Chocolate chip cookie. No, plum pudding.
Rutherford.
Nuclear.
So where are we at now?
So we're not actually going to further our models of the atom today. Today we're going to get a little sidetracked and talk about electromagnetic radiation. And that's going to lay a good foundation for future models of the atom. So let's get started. Atomic History Part 3.
More epicness.
Electromagnetic Radiation, a lesson from the Atomic Theory Unit. Electromagnetic radiation, EMR. Properties. It's also known as radiant energy, remember from matter and energy. Has wave properties, like wavelength and frequency. Carries energy through empty space, no medium is needed. This is like how energy gets here from the sun. It also travels at the speed of light.
Here's an example of what a wave looks like.
The electromagnetic spectrum. It includes all different wavelengths of light, most of which humans cannot see.
If we take a look at the electromagnetic spectrum, we see on the left where there are radio waves, we have a very long wavelength, which actually means a very low amount of energy. Continuing towards shorter wavelength, higher energy, we move up to microwaves, infrared, and then to visible. Now visible light would be light that humans can see. Notice it's a very tiny band there. We even have to expand it out to see the different colors. We continue moving, we get ultraviolet, X-ray, and gamma rays, again with a shorter wavelength and higher energy. Quantized energy. Let's begin by talking about continuous energy. If EMR had only wave properties, then energy would be delivered continuously. In other words, it would build up over time as the wave passed.
Now this continuous delivery of energy can be thought of like an escalator or a waterfall, where it's constant, it's smooth, and it's continuous.
Quantum energy. If EMR had particle properties, then energy would be delivered in a specific amount all at once. Think of a quantum of energy as a ball, chunk, or package of energy.
So quantum energy, unlike continuous energy, is all at once. Bam! Continuous energy was like that escalator, continually bringing you all the way to the top, where quantum energy is more like a staircase. When you're on one step or the other, there is no in between. You go right from one to the other. All that energy all at once. Or if continuous energy is thought of a waterfall where the water is constantly coming over, quantum energy can be thought of as someone instantly dumping an entire bucket of water on you. Max Planck, German physicist, 1858 to 1947. Max Planck made the observation that hot objects give off only specific types of EMR. He deduced that the energy was only being released in specific amounts and was therefore quantized. A quantum of light is called a photon.
Albert Einstein, German physicist, 1879 to 1955. Einstein explained the photoelectric effect. When EMR shines on a metal surface, an electron can be ejected from the metal. Because EMR has wave properties, it was expected to continuously build up enough energy to eject the electron. Instead, it was found that EMR of a specific frequency ejected the electron, regardless of the EMR's brightness or intensity.
So if you take a look at our examples here on the top, we've got three different frequencies of light. We've got red, green, and blue. The red has the lowest frequency of light, and as you can see, no electrons are being ejected from the metal it's being shown onto. Now, even if that red light was much brighter, we still would not get any electrons ejected. Now, if we move all the way over to the blue frequency, we have a much higher frequency of light, and that is in fact ejecting electrons. Even if the intensity of that blue colored light was very dim, we would still eject electrons. Einstein won the Nobel Prize in 1905 for his explanation. A specific frequency is needed to eject the electron because it delivers a specific amount of energy all at once, a quantum of energy, or a photon in this case. Frequency below the minimum, no electron ejected. Frequency at minimum means that electrons are in fact ejected. Frequency above the minimum, electrons are ejected at a faster speed.
Students often get frequency above the minimum and intensity kind of mixed up. So just to reiterate, if we are above the minimum frequency, that electron is ejected faster. If we shine high intensity light, this just means that more photons are delivered and more electrons are removed, not necessarily at a faster speed. Let's try to illustrate how this photoelectric effect really works. Let's say I have red light. Now let's start thinking about that light in terms of photons. It's a package of energy. I have a package of red light. I deliver it to my metal surface, it hits, but it's not the minimum frequency or minimum energy to eject an electron, so nothing happens. Let's move up. Higher frequency, higher energy. I have green light, so this is a green photon. Boom, it hits, an electron gets removed. It's got a certain speed as it's removed. Now I go even higher frequency, higher energy. This is blue light now. It slams down. Now I remove one electron again, this time at an even faster speed. And if I had high intensity light, that would just be more of these photons hitting the surface and more electrons being removed. This animation will nicely illustrate how the photoelectric effect works. We're gonna shine light from this lamp here at a metal surface and see if electrons can be removed. Now we're starting out on the red end of the spectrum. This is low frequency light, so this means low energy. I'm gonna increase the intensity of the light because it's not even on yet. And I shine it on the metal surface. I don't see anything happening. This must mean that this low frequency, low energy light is not carrying the right amount of energy to remove an electron. So if I increase the intensity and go all the way up to 100%, so brighter red light shine on that metal surface, still will not remove any electrons. And again, that's because if light is quantized, it's carrying a specific amount of energy and delivering it all at once, and red light is not carrying enough energy to remove the electron. All right, I'm gonna go back down to a little bit lower intensity. Let's raise the frequency now. Changing the color of the light. And eventually, I hit a frequency that is carrying the exact right amount of energy to remove electrons. So electrons are coming off that metal surface. Now, if I increase the intensity of this light, that just means there's more photons hitting the metal surface. And what I should see is not that the electrons are actually moving faster, but that there are more electrons being removed. This is because more photons are hitting the surface, and so more photons means more electrons are being removed. All right, now if I continue to increase the frequency beyond that minimum, I'm delivering even higher energy photons. So at the same intensity, I'm removing the same number of electrons, but that higher frequency with higher energy means the electrons are removed with a higher speed.
In conclusion, EMR is quantized and thus has particle properties. EMR still has wavelength and frequency and thus has wave properties. This is called wave-particle duality. In case you missed it,
let's revisit the idea of continuous energy. Continuous energy eventually builds up over time. I've got a good analogy here for you. Let's think of a vending machine that sells pop and it says change gladly accepted. That means we could use any coin amount, and as long as it added up to the $1 that the pop costs, we'd eventually get our pop. We can build up the amount of money, like energy, over time to get the pop out of the machine.
Quantized energy is all or nothing. So continuing on with what Shu just told you, if we have a similar vending machine, but this one only takes dollar bills and doesn't give change, it doesn't matter if you have 2 quarters, 4 nickels, and 3 dimes, you have to have that $1 bill to get your soda. It's all or nothing.
That's going to do it for today's episode on electromagnetic radiation.
Later, nerds!
Today's episode is brought to you by
Photon luggage for when you're traveling light.
But we never off, always on to the break of dawn. SCIENCE in the hall they call S-Wing. You know we never wear a tie like my homies, boys to men. It's so hard to say goodbye.
Like this, that, and this, and it's like that, and like this, and like that, and it's like this.
You're going in low power mode.
Plug and chill to the next episode.